But in the AI world, you need big data, and the problem in the semiconductor world is you have small data. Data is very expensive in semiconductor industry. To give you a perspective, you need like million simulations to get a model right. Like if you look at Facebook problem of recognizing cat, you actually need like tens of million photos of a cat to make sure that it's a cat, else you show a picture and it's going to tell you it's a room. In semiconductor industry, a wafer costs you $20,000. So it's not practical. So we deal with big problem with small data. Yeah, once the flywheel is in motion, then it's like it just picks speed.
How many are you going to get to? Are you going to get 200 patents?
I don't know about 200, but I do know that I have 15 in works right now. So my three core principles: innovative thinking, second is empowering people, third one is shared success. If you put your head together and look at any problem, there is always a better way of doing it.
Arvinder, let's switch gears a little bit around the topics of AI, specifically applied within the semiconductor manufacturing space.
Almost every company is making their own tools based on the inferences that the AI models are predicting to either prevent or decrease the amount of electricity by not running things when they are not really required. It's similar to like what we would do in the house, right? If you're not in the house, you unplug things or don't keep things on. So people are doing things like that. I guess the other thing I would say is that just go do it. Like, don't ask for permission, ask for forgiveness.
Welcome to today's episode of the Inference show. Today we are delving into the cutting edge of semiconductor manufacturing, AI-driven process optimization, and emerging semiconductor technology trends. Our guest is Dr. Arvinder Chadha, a seasoned leader in the semiconductor industry. Arvinder currently serves as the Director of System Engineering at Applied Materials. At Applied, Arvinder works on semiconductor equipment development for next-generation wafer requirements. Arvinder's background spans advanced R&D in nanophotonics and optoelectronics, product and supply chain initiatives, and strategic application of AI in manufacturing. Arvinder has 19 granted patents, numerous publications, and hands-on experience steering teams from concept to market. Today, Arvinder will shed light on the next wave of innovation in chipmaking. Arvinder, welcome to the show. Let's dive right in.
Thanks for having me over and for the kind introduction.
Arvinder, we were looking at your profile, and you started your career in nanophotonics and optoelectronics, and then from there on you moved into semiconductor manufacturing. What sparked your interest in electronics and semiconductor technology?
So I would say, like, ever since I was growing up, the concept of electrons and duality of electrons really interested me, like how an electron can act both as a particle and a wave. And then I just went ahead, got my master's in solid state physics, where I learned about optics, electromagnetics. And then I took a class in semiconductor manufacturing. And that was very pivotal in my opinion. In that particular class, we started by designing a circuit and then manufacturing it and testing it. And then the whole level of complexity changed from, like there were too many challenges, too many complexities, and I found it very stimulating. And then that's how I pursued my path in semiconductor and manufacturing.
Interesting. So then the key point was that class in solid state physics?
Yes.
That was the pivotal moment for you?
There were a couple of pivotal moments. Like in like my original research was in metamaterials, but then it was, I think, I would say really the hands-on fabrication class where we leveraged the things that we learned in like the physics of the devices, but then like how things are actually made, like a transistor, which is the heart of any electronic machine.
You said something very interesting, that early realization that electron could be a wave or a particle. What gives electron that capability, Arvinder?
I think It's like it goes back into like the first principles. You
Yeah.
may have heard of the Thomson-Crompton effect, and it's really like how uh, at a very fundamental level, there is a wave particle duality associated with it. And what it says is that if you shine an electron through a wall, it can actually, there is some finite probability that it can pass a wall. And it's very counterintuitive. Like typically, if you throw a ball on a wall, it will almost certainly never pass the wall. But different things happen at a very small scale, particularly when the size of your object is similar to the wavelength of or the energy of this particle. Then you start seeing quantum effects, and that's what makes the whole fundamentals way different than the classical mechanics. And so it's really at the very fundamental levels. When you look at the energy and the size of the particles, then new novel features emerge.
So those same principles are at play every day in the semiconductor devices that we use and play around with.
I would definitely think so. I mean, a simple example would be your like transistors. You may hear of like the older generation transistors and the newer nodes. The whole uh, industry is moving from like 65 nanometer nodes, which means like how far the source and drains are inside the transistor, versus now they are going to like 2 nanometer or 3 nanometer or sub 5 nanometers. What that really means is that the dimension between your source and drain are so small that they're comparable to the electron wavelength, and it's very difficult to control or manipulate the on and off state. So we are definitely seeing that every day.
So the gate length is then approaching the those numbers, right? Where
Right.
understood. So it was definitely that key course on solid state electronics, and then you were at UC Boulder, you got your master's there, and then you got your PhD at UT Arlington. Were there any other key moments or milestones from your academic journey that shaped your technical perspective in these areas?
Yes, definitely. So during my master's, it was the fabrication class. And then for a brief stint after that, I was working on making micro robots for minimally invasive surgery. So there, I explored transistors, the heating of the transistors, which is pretty much detrimental in the conventional electronics. But the idea in our case was like to use these heating from the transistor, on demand heating, because you can have a digital logic. And then if you were to put it on a shape memory alloy, this is a special kind of metal which can deform based on the amount of heat you give. So the project was basically design your own transistor and control circuitry, and then bond it to a shape memory alloy, and then through control of this electronics, you can make the robot bend and move so it can navigate through your arteries. So then I honed into bonding. I got some bonding experience, and then I went into product uh, productization of individual components that are being used in 3D silicon photonics and heterogeneous integration. My PhD was on making these components for next generation photonics chips, which are now mainstream in the data center applications.
What were some of the other bigger surprises? And you were like super academic, top programs. What happened? How did you feel, and what did you see when you moved from academic research into R&D?
Yeah, definitely. I think so. There are similarity and differences. So similarities, I would say, like at least in my case, my professor always grilled. Question one was like, why are you doing this? And second is, after you have explained that, then you make things, and then if you fail things, like if there are failures, he emphasized on like, why did it fail? Like, what's the real root cause? So I think I would call this as critical thinking. Like, you need to know why you're doing this, and what other things exist in the market. And then once you execute, how would you fix it? So this critical thinking is very transferable to industry. So that's the easy part. The new things were like, and typically in research, you work solo most of the time, whereas in industry, the concept of solo does not exist. You have to talk to the product managers, you need to talk to supply chain folks, you need to talk with business people, and there is a lot of team dynamics, and you'll meet difficult personalities, and just like working with different people and relaying technical information to non-technical people. So that was something quite interesting.
So you went from an individual researcher, primarily an individual contributor, to really doing great in the industry. You're currently a director of systems engineering. So that meant that learning to work as a team and driving team performance, innovation as a set of together as a set of people rather than an individual. It also perhaps meant being a leader, right? So can you tell us a little bit about how did this evolution come to be?
The way I grew my leadership was like when I came to the industry, you have to build your own credibility for people to listen to you. So that was the first thing, which was very obvious to me, that if you want to get things done, people have to trust you, to listen to you. So the first thing, I would call it more of a personal development, where you build your technical competency, so you understand your product and the challenges associated with it. And then you have to think of your problem holistically, that you need to have a big picture thinking, because this product that you're working on is going to talk to something else, something bigger. So you need to look at both upstream and downstream processes. So once you give this holistic idea and you give recommendations, so people who are present in these meetings where you're proposing your solutions, they know that you have thought through all of these things, and the trust is built, and then therefore they'll let you do things. So then when I became a manager, and then more of a supervisor or whatever, then I learned that I did a similar thing in a way. What I did was I spent more of my time in strategic thinking to identify like where we should go. And then in doing so, I also worked on delegating some of my activity, because me working on something means something else is not getting worked on. So you need to delegate stuff. And lastly, I would say, you know, uh, building the people and empowering them to do things, and whoever you delegate this activity to, you need to like empower them.
Arvinder, it seems that you've thought about this model around, you've thought around this model of success. So you've talked about innovative thinking, empowering leadership, and a commitment to shared success as your core principle of working. So obviously you've thought about this and encapsulated it into at least three principles. And you talked about those. Can you shed a little bit more light into why each of these are important and how do they combine together?
Sure. So my three core principles: innovative thinking or innovation. Second is empowering people, and then the third one is shared success. I think if you put your head together and look at any problem, there is always a better way of doing it. And that better could mean better performance, lower cost, better productivity. So I always challenge the status quo. And whenever I have a new employee, I always ask them, or any, for that matter, any meeting I go to, I always ask, what are the other options of fixing this, right? Which is the most efficient one. The second one is empowering people, because when you delegate things to other people, you are in a way not only simplifying your work so you can spend time on other activities, but you're also shaping the career of these other people, so they are given more difficult tasks to do, and they can learn and grow, by which it could mean like getting them access to some software license, or maybe buying an equipment for them so they can test something. But at the end of the day, it's like if they feel empowered, then they're willing to take more risk. And I always promote a culture where you take risk, fail fast, and you don't get rewarded for like failures, because it's always an way of like growing faster. And lastly, I don't think only like one person can solve any problem. It's always a group thing, and therefore I believe in like giving credit to everybody who touches the project, even if it's in like different capacities, but giving acknowledgement to everyone, and then relaying the message that everybody's work is important in getting things done, and then connecting their role to the corporate objective, so they have the sense of belonging, and then that in turns make them motivated and prioritize things on their own, and eventually shape themselves better.
Interesting. You talked about the fast changing pace of industry, and that really seems to be the case with semiconductor right now. Semiconductor has suddenly become very important. The pandemic altered supply chains. A lot of those issues came out, but with AI and large deployments of AI, semiconductor has become, it's going faster than ever and changing as well. What are the most significant shifts today that are shaping the industry right now?
I think there are a couple of things. One is, you hear AI everywhere, so clearly people are using AI to develop their designs. They are using AI to make sense out of the data, which has resulted into yield management, developing new processes so you can have better, less defects, preventive maintenance, so your downtime of your tool is less, and hence your cost of ownership is better. They are using AI for solving tougher problems, because earlier the infrastructure wasn't there to run these complex models. As an example, people are using it for computational material. What it means is that what is the best gas recipe that can give me, which can define for me a etching or a deposition recipe where I can get near 100% of my devices to be working perfectly. So there are a lot of innovations in the area of AI itself. With reference to supply chain, with the COVID happening and now the geopolitical tensions,
Yep.
I think that has led to industries looking into dual sourcing, some risk management in terms of like having it used to be just in time, but now I think that mindset is shifting to like having a bulk stock on hand. So to enable like a burst demand or a COVID situation, having a better ERP system so you can predict better. And pretty much I think these are the seismic changes that you will observe.
Arvinder, a lot of our audience is highly technical, but there are those senior leadership amongst our audience that may not be that technical when it comes to semiconductor manufacturing. If you can give us a short overview of the core pillars of semiconductor manufacturing, for example, lithography, etch, deposition, metrology. What are those? How do they connect? A short tutorial in a few
Sure.
minutes would be very powerful to educate our audience there.
Okay. So you made my life simple, and you said it right. On a very high level, semiconductor manufacturing is essentially lithography, etching, deposition, and metrology. So think of lithography as photography, where you take a picture and then it's imprinted. Similarly, in semiconductor world, what it means is that you start with a wafer, you deposit with a photosensitive material, you shine light on it, and it forms patterns for you. and then after you develop them, the patterns are formed. So now you have a film with holes in it where you can now start doing the next thing, which could be etching or deposition. Etching is like what a like in a when you make a sculpture, they might be chiseling away the unwanted things. So etching is basically doing the thing of removing material out. And then deposition is like making a cake. You have layers, you add layers of, it could be cream, it could be fruit. So similarly, deposition is basically, it could mean depositing metals or oxides or semiconductors, all have different purposes. And then metrology is basically the science of measurement. So in metrology, you're measuring how much have you removed, how much have you deposited, what is the concentration or the property of the material that you have deposited, because all of that impacts your device performance. So in a nutshell, semiconductor manufacturing is a repetitive sequence of etching, lithography, etch, deposition, and metrology.
Now, this seems to be very complex because on the size of a dinner plate, you're building structures that are, we talk about the gate length, the distance between the source and the drain being nanometers now, right? So there is going to be, defect, there's going to be yield, there's going to be uniformity issues. Can you tell us a little bit about, key principles of lithography, etch, deposition, metrology to actually get the wafer to work?
Right. So in all of these processes, what you care for is uniformity. So whenever you put a wafer, it's sitting on a pedestal. Or if you are doing etching or deposition, you're inside a chamber where there is plasma. Plasma means you have high vacuum and then you are generating heat and gases are flowing around. So you need to manage all of these controls, like your temperature should be uniform, your pressure should be uniform, your flow rates of the gases should be uniform. Or if they are not uniform, you should have a logic in your system such that you can compensate for these non-uniformities so that you can have a uniform performance. And you do this by, there are like tons of sensor on your chamber which you can monitor in real time, and based on the readings you can control them. So that's how you would achieve uniformity on the wafer. Even if you do all this, you will almost never get 100% yield. So for yield management, how do you manage yield? You get yield losses because there are defects. So let's talk about defects for a moment. So the defects can come as a part of unwanted things sitting on the wafer while you're doing these processes. So there are very tight controls around the clean room environment. To give you a perspective, sometimes you'll hear class 1 or class 100. What it means is that you can have only one particle in like a square foot of area. Or class 100 would mean 100 foot. And then within the chamber, you're doing these processes, like you can get a coating deposited on the sidewall of your chamber, which may like flake off and come back on your system. Or it may be that your gases are so toxic that they are eating away the material that they see inside your chamber, and then they go and land on your wafer. So the way you would manage all this is by using better materials which are more resistant to the gases, toxic gases that you're using, or implementing very tight cleanliness environments, developing recipes so that you don't form these defects, unwanted defects. And then yield, you manage by analyzing the data. There may be systematic shifts, and if there are systematic trends that you see, you can compensate them by your design change, or you can change your process to eliminate the systematic shifts. The unsystematic ones are the troublesome ones.
Yep.
And if you can find, if you can lower these unsystematic defect areas, then you can maximize for your yield.
So you have this wafer then that is being processed, right? So you do lithography and then you take it to a different chamber. What is the typical flow and how many steps are there until you go from wafer to, dies that need to be cut out? How long does it take, Arvinder?
So typical tape out process would imply like depending on the complexity of your chip, it could have like 200 steps of etch, dep, litho. There are other steps we didn't talk about, like you have implant, you have chemical, mechanical polishing, and so on and so forth. So all in all, you have 300, let's assume you have 300 steps. And typically in a fab, you can do 3 operations per day. So if you do the math, you're looking at for a one full chip to come out from silicon to a chip, you're looking at roughly 2 to 3 months time. And if anything goes wrong in between, you basically lost time and money. So it's it can be very stressful.
And on top of this, there are new material breakthroughs, process technology that's changing, right? So there's a lot of new change that is being brought up in manufacturing today. So what's going on? Are there new material breakthroughs happening? How is process changing?
Right. So semiconductor is going through this tectonic shift. The next generation, the things you hear are quantum computing, you're hearing advanced packaging. I think in terms of material breakthroughs catered to these elements are, let's say, quantum computing chip, right? Typically, they use cryo-based systems to do quantum processing. And a typical cryo machine is like a size of this room, but then you need cooling to cool that, which is probably like 2 other rooms to provide the infrastructure to do that. So there is another way of getting rid of it by doing it on silicon. So when you go onto the silicon, you can basically have like a rack versus having this large machine. So there, the material innovation is like how you can make a better silicon dioxide to silicon interface. So that's one area for ripening. In terms of advanced packaging, it's about like lowering power consumption, increasing performance, decreasing area, and decreasing time. And the way you do that is by decreasing the latency, decreasing the joule losses. So we are trying to find materials which have lower resistances. And then since we are doing vertical stacking, so how do you engineer the interface of these materials so you have good adhesion so they don't delaminate when there is a heat load when they are in work. So people are exploring new materials. How can they change the surfaces of these materials so the adhesions are good? And then instead of going vertical, there is another school of thought that can we go horizontal, which is currently being like Moore's law says that you can keep going like smaller in size, but you hear that 2 and 3 nanometer is giving you very low yields. So another way of getting around it is using 2D materials. So that can open up new way of like scaling in the XY dimension versus going upwards. So I think these are the high level material trends.
Interesting, Arvind. There's a lot going on because on the quantum side, silicon is then an interface to the quantum that truly runs at close to 0 Kelvin, right? I mean, that's the goal, right? So the interface materials at the interface point is from what I understand, right? And on the other side with integration and chiplets, right? I mean, chiplet seems to be a big trend there as well, right? Trying to push the continuity of Moore's law through planar innovation. So if you can elaborate a little bit on the last one.
So in terms of scaling in the XY plane, you may have heard of like gate all around as the next successor to like FinFETs. You get some scaling, but then if you go to like 2-dimensional materials, so these are like, think of atomic layer films, and then the mobilities since you are in a two-dimension in atomic level, the quantum effects kick in, and then now you can have ultra-fast performance material, and you can get much higher speed of communication. So that will help you with giving you low latency devices. Because if you go in the 3D stacking, firstly the devices are large, and the time it takes to go from like the starting point to the end point, that time will be orders of magnitude longer if you were to compare them against 2D materials. However, 2D materials are not very easy because you are depositing like literally like one layer of, so you are trying to control your deposition in angstroms level. Forget about nanometers. You are an order of magnitude even lower. And typically people talk about like microns when they manufacture. So there's a paradigm shift in doing these depositions.
So you have this complex process that goes on for a period of few months. You have a batch of wafers coming in, say 200 steps or more onto it. So how do you make a supply chain resilient when it is such a complex process, Arvinder?
I think historically supply chain motto was like vertically integrated, meaning you do everything at one supplier, so your costs are low, and you have strategic partnerships with a supplier at a given location. But now that is changing. You cannot have that model anymore. You need to have dual sourcing. You need to have strategic partnership with people, and it may also mean that you invest locally because of the geopolitical issue that is quite unstable right now. So people are looking into that aspect of things. Then it used to be all about just in time inventory management, which meant that I know the lead time of my material, so I can get them just in time, so I'm paying less money because the cost of operation is lower. But you can't do that anymore either, because if you do that, good example is COVID. You cannot have enough capacity, so there's a big backlog of parts. In fact, it typically took in general, it took the industry about 1.5 years to get to like the normal level. So now people are working in collaboration with the suppliers to build their capacity so they can house like more inventory, or at least have the capacity should the order be placed so they can make it fast. There's another thing which is kind of underlooked, but people are trying to forecast better because it's such a volatile industry and such a high pace industry that if a breakthrough happens, your older generation will become like obsolete very quickly and people will pivot to the next best thing. So you need to like forecast a little better.
But who would have forecast what happened in AI, right? Or demand, right? So those are the interesting bits, right? So it seems that more collaborations are important today and more partnerships.
Right.
But how does that happen in an industry that has traditionally competed?
Right. So
Right.
that's a very big problem. You want to collaborate, but you don't want to share because people fear that it's my IP. My IP gets
Yep.
leaked, and IP comes in various form. It could mean your drawing, it could mean your volumes that you're expecting, and so on and so forth. So, so actually, there is a big emphasis on having trust and collaboration with suppliers, and it requires a mind change of like a win-lose situation to a win-win. And historically, people used to keep everything to themselves, and that model is not going to work. You have to give something and co-innovate for this model to work and for you to succeed and have the products to market faster.
Do you think it will lead to more open standards and things that are, the traditional equivalent of open source? Or it'll be closed groups working together?
I think unlike I would probably say no. uh, there are things that could be common, like the industry may form. If let's say if some supplier finds a very nice material that is resistant to plasma, I think that material will then become the new standard for the industry. But the design of that material, or the design of the component, that will not be same, because it's because you have whole fleet of machines that are built in a way that talk to each other. So I would say yes and no. Like, some elements will get prolificated, most of them will not.
Okay, interesting, Arvinder. Arvinder, let's switch gears a little bit around the topics of AI, specifically applied within the semiconductor manufacturing space. So, we've heard that AI is increasingly used for predictive maintenance, yield management, process control. You know, have you seen the transformation in the day-to-day operations on the factory floor today, or how is it changing?
Yeah, so I think one of the biggest thing I'm seeing is that people are they're starting to use the data that the tools have already, because earlier there are sensors on these tools, but people didn't pay attention to these things. But now they are looking carefully at how the consumption, uh, how the electricity is being consumed, how the gas is being consumed, and so on and so forth. So now almost every company is making their own tools based on the inferences that the AI models are predicting, to either prevent or decrease the amount of electricity by not running things when they are not really required. It's similar to like what we would do in the house, right? If you're not in the house, you unplug things or don't keep things on. So people are doing things like that. People are also looking at trying to find trends through this noisy data, and that's giving them insights that, hey, it's time for you to do preventive maintenance. So it could be that you can delay it, or do it at a faster rate. Both of them have merits, in the sense, if you do it faster, then you're not having scrap, versus if you're doing later, then you are not really overdoing your maintenance, in which case you're using your machines efficiently, so your cost of ownership is high. So all these things are happening in the manufacturing world, and several more things that are happening.
Do you see applications or success stories on a daily basis,
Well,
or
it's
on the
not,
floor?
yeah,
Yeah.
it's definitely not daily, because just training these models can be time consuming. But if you look at like Gartner reports, or any of these McKinsey reports, it is very, uh, even if you do a quick Google search, you'll see on an average 15 to 20% improvements with basic assessment. Uh, you can get improvement in forms of productivity, or yield management. So this is quite common now. In fact, there was a journal paper in Nature by Lam Research, which showed that if you augment AI in developing recipes, you can save money. So AI, what you will notice is that you need human intelligence to screen on a high level the right combination of recipes, but then you can leverage AI for fine-tuning the knobs. So if you augment the two, there can be a lot of cost savings and time savings.
So you have this complex process where you have tons of data coming in from metrology, from process parameters, equipment logs, all the sensor data, and all of that you're using the AI to make decisions, with humans trying to prune the tree, the highest level branches, and then AI making sub branches or paths that are the best choices for that particular application, or choice of for that particular application of the tech, right? Did I get that right?
It is So human gives the high level lay of the land, and then AI does its thing, and then the human reviews that data and tells which branch to proceed in, and then the AI will give you more focused routes, and then so you need like periodic human intervention to like get it right. So
Okay.
it's yeah.
Okay. So obviously this is not a closed loop system right away, right?
Right.
So this is not happening in real time, right? So this is analysis that happens, or have people also developed more closed loop systems that can give feedback, or is it over batches of wafers over months that these
Right.
iterative improvements happen?
Right. So I think the holy grail is closed loop, but in the AI world, you need big data. And the problem in the semiconductor world is you have small data and it's expensive. Data is very expensive in semiconductor industry. So so the models are not perfect. To give you a perspective, you need like million simulations to get a model right. Like if you look at Facebook problem of recognizing cat, you actually need like tens of million photos
Yeah.
of a cat to make sure that it's a cat. Else you show a picture and it's gonna tell you it's a room. So in semiconductor industry, a wafer costs you $20,000. So it's not practical. So we deal with like big problem with small data. So you have to be intelligent about how you are doing the data processes, and our tolerances are like 1 nanometer, things you can't even, they are very tight and difficult to measure. Uh, so people are working on how to augment the model. You can create your own data to augment the actual measured data, but it's gonna be a while until something can be closed loop in the semi world for a process optimization perspective.
So then the primary challenge is lack of data, because each wafer, as you said, is 20,000, or
Right,
somewhere that number. So it's not like they have a million cat images lying around,
right,
right?
right,
That they could train upon.
right. But with that being said, with whatever data you have, and if you understand AI implementation methods, there is room for improvement to standardize your data collection so you can be forward looking if you were to implement that. And there are cases where, with whatever images you have, it helps you with troubleshooting issues faster. So there is definitely, although you don't have like a performance solution, but there is a productivity impact already that we are seeing.
So a hybrid approach that is dictated by an ROI for the business leader is imperative. And then you obviously need people. So once the business leaders see that ROI, the AI still needs to be implemented, and then leads to verification of that ROI. Do you see semiconductor manufacturing companies in the space hiring more AI engineers today? And how do people collaborate? This is a new function suddenly that appears, right? So you
Right.
have process engineers, you have operations people. So what is a good working model for all of them to collaborate together?
Yeah. So it's actually difficult because, firstly, you have Googles and Fangs of the world, right? So they are wanting to go there versus coming to a semi industry because of the pay, right? This is the truth, right? And they sound sexy. So we have to deal with that reality. The second one is so when we do hire them, they need to have passion towards semiconductor. I mean, nothing can beat passion, right? So if an AI engineer is trying to come to a semi company, he needs to do two things. One is he needs to have hands-on AI experience and the coding skills needed. But I would also say that it will be beneficial if he knows about semiconductor manufacturing. And I think both of the skills can be taught on the job as well. And then there's a need for soft skills as well, because you can do the best work in the world, but if you can't communicate, then who cares, right? So I think the engineer or any person should be able to have communication skills which can make it easy for the decision makers to make decisions, and should be a team player, because you cannot be a one-man show in any company. It's not going to work.
Yeah, I mean, this seems to be a pretty complex problem. On one side, you have a hiring problem because the FANGs are taking away all the AI engineers, right, amongst all the AI startups that are out there. And then you need this deep domain knowledge, right?
Yeah,
Or a willingness to learn that,
right.
right? So most of your AI engineers, then do they start out as AI engineers, or do they start out as process engineers? You're curious about AI and then end up doing AI.
Right. So I think we have a variety of engineers. Sometimes we outsource some of our projects through IT service companies. Sometimes, these companies have their own internal development programs, and people who are motivated, and depending on the manager and the employees arrangement, they get trained to do uh, take classes in software or AI. So typically, the companies support them in development, and then they give them hand projects to get hands-on experience, and then they can deliver better.
Interesting, Arvinder. I think those are awesome insights around using AI in semiconductor manufacturing. Let's go back to semiconductor itself. So there's this continued push still towards smaller nodes. A lot of people said that Moore's law is going to break down. Hasn't happened till now. There are emergent architectures, chiplets, advanced packaging, 3D integration, more things that you talked about. Where do you see this go, and what are going to be the largest enablers next decade?
Yeah, I think definitely people are spending a lot of time in 3D integration. So instead of scaling laterally, they are scaling vertically. And the big challenges in scaling vertically are material challenges, really, which are basically, do you have a material which will dissipate less heat? Do you have materials that can make things stick together? And then as you go vertically, your wafer, which used to be flat, typically a silicon wafer is like very flat. But now, because of these integration, things get like bent. So then how do you manage clamping or keeping the wafer flat when you're doing etching and deposition? Else, if you do these processes and in a deformed state, then you get non-uniformities and hence yield losses and hence meaningless devices or very expensive devices. So a lot of development in the area of how do you manage like warped wafers, and the substrate could be different than silicon. Then how do you manage non-silicon devices? I think these are the areas where people are working on. And then on the device side, they're working on architectures as to how you can consume less power, so your battery life can be longer, your heat dissipation can be smaller. So there are like design architectural changes that we are seeing in the industry.
Yeah, I mean, FinFETs gave a lot of advantage in in power, right? In passive power or power not being used, right? So you'll see that kind of innovation
Right.
continuing, right? Okay. Arvinder, in looking at your profile, one thing that really stood out that distinguishes you is the numerous amounts of patents and intellectual property that you've created. So you have what, 19
Yeah.
US patents now, and I don't know how many invention disclosures. Uh, what was your first one? And I'm sure we can go look that up in public.
Yeah.
And how did it come to be?
Yeah. So my first one was on display. It was about making 3D, like using nanometer scale features, but on a large area and very fast. So typically we make nanometer scale patterns using e-beam lithography, which is very, very, very time consuming. To give you numbers, it could be like few days if you were to pattern a whole 300 millimeter wafer versus my project was related to making wire grid polarizers for TV, and the goal was like, how can you make like nanometer pattern on a TV scale form factor? So if you were to do that with e-beam, well, first the machine can do e-beam on a TV scale form factor because typically e-beam machines are for silicon wafers, so 300 millimeter. And let's say if you were to make one, it's still going to take you a couple of months to make it. So my invention was basically using optics to enable large area nano patterns within like seconds to minutes. So pretty fascinating. I used first principle of optics in creating these periodic patterns on a large area.
Interesting, Arvinder. So, you saw this problem or something that was out there, and then you thought about how it would happen, right? And then you replicated that process across the various problems that you saw in the future. Like, how did you end up with so many patents? I mean, that's so remarkable.
Yeah, so I think there are two ways of creating patterns. One is if there is a known problem, then you can find an innovative way. By innovative, I mean it should be differentiated, something different, else you can't file a patent. And the other is like, even though you have this innovative pattern, you should be able to make it like efficiently, repeatability. It should be sustainable. So if you have like a differentiated and a sustainable way of making it, then that's one way of making a patent. And these are all geared towards like a known problem. The other way you make patents is by hypothesizing, like you look at industry pain points, or you can anticipate what the industry would need should something be covered by some other process. So if you do some forward looking, then you can file, you can make a quick proto, validate your theory, and then you can file a patent. So these are, in my mind, two broad ways of filing patents.
So one is then the better solution to an existing problem,
Right.
and then looking, predicting what might be new problems and solutions for them, right?
Yeah.
Those two
Right.
approaches. So, both of those approaches can yield an idea. How do you develop it and make it patentable?
Right. So first is you validate that you are actually solving a problem. Then you find the root causes, like why is there a problem, right? Then you have multiple solutions and you will have a preferred solution. Then you can either screen that idea by doing some modeling to get some results, make sure it makes sense, and then you make a prototype and see whether it's going to work or not. Let's say if you're trying to make like a very large, like for example, in my case, if you want to make this nanoscale pattern on a TV form factor, I don't need to start there. My concept was to use this grating and light, broadband wavelength lights to make sure that it can give me large area. So I started with a small coupon, because once you prove your fundamentals, then the rest is an engineering exercise that you can scale, and we are an engineering company. So that's the easy part. So I would just say make a minimal viable product to screen your ideas, and once you have this, you file a patent.
How long does the process usually take,
Yeah,
or how long did it took you?
Yeah, so typically it can take you from a year to few years, and there are two kinds of patent. One are provisional patents, and the other are called non-provisional patents. So non-provisional one is the one that actually gives you a patent after it's being reviewed by the patent officer. For a non-provisional one, what it means is that you file a patent and then you have 1 year time frame until which you have to file a non-provisional one. So the purpose is that during this 1 year, if you come up with something, some new idea, or if you can improve your method, you can then file it. You can add it or edit your existing draft, and then you don't lose your priority date. And that's how the that's how the provisional ones work.
In terms of process, Arvinder, I'm personally very curious about the process. In my past life in industrial research, we filed a lot of patents. I wonder, do you have a process to it? I don't think anybody gets to 19 patents randomly. So you must be constantly thinking about it, because you said that it's something that lasts 1 to a few years, right? So
Right.
you must always have something in the loop going on all the time. Do you like allocate certain day of the month to work on it, or what's your process?
Good question. I typically promote like 10% time in thinking creatively. But then again, I personally think all the time about work. So there are too many problems to be solved. So I'm always thinking about something, and if an idea sticks, then it's about getting the resources to do some preliminary screening. And if you get good results, you go ahead and file the idea. So it starts by filing an idea, then there is a patent committee, which are experienced senior people in the company.
Yep.
Then they decide whether it should be filed as a patent or not. And then if it's valued, and if there is a business value to it, cost, performance, yield, then it gets filed. Sometimes it could be as simple as like blocking other people and doing things differently.
Yeah, yeah. Now, your model of filing patents, is it more, do you do it individually, or do you work together as a team with other people who may share a common interest in solving that problem?
Most of my patents are with somebody, because, like I said, you can almost never do things alone. So sometimes you have an idea which you are working on in your field, but then there are times where you hear the problems from somebody else, and although you're trying to help them, then you solicit their ideas, their thinking, and then you come up with a common solution.
Understood. So going back to your your core principles, I think again I see those repeated patterns. So innovative thinking. So you mentioned that you're always thinking, right?
Right.
Your wife must not be too happy about that, though.
Nope.
Okay, you got to do what you got to do.
Yeah.
So innovative thinking, empowering leadership. So it seems that you're working together as a team to make a progress, and obviously show a commitment to shared success over there, right? Because everybody, has rights to or benefits,
Right.
from what they've created, right?
Right.
And then you do that over a period of years, working on an idea, and you have several in flight, right? So,
Right.
is that the orchestration model?
Right.
Have we decoded your secret, Arvinder?
Yeah, I think it's pretty much the same three things over and over again that you will see repeat.
I think the key is to putting in that effort over the period of years to make it happen, right?
Yeah, once the flywheel is in motion, then it's like it just picks speed.
How many are you going to get to? Are you going to get to 100 patents?
I don't know about 200, but I do know that I have 15 in works right now.
Awesome.
Yeah.
That's so awesome, Arvinder. Congratulations.
Thank you.
So we're approaching towards the end of this fascinating conversation. Arvinder, what advice would you give to leaders, young engineers or emerging leaders? What are things to watch out for in the semiconductor manufacturing space, in this world that is more driven by AI today? So, what are the key things that one should really care about?
Right. So I think the advice would be different for leader versus engineer. For a leader, I would say start with the business case. Like really make sure that you're gonna get money out of it or productivity, whatever that is. And then keep in mind that um, implementing it is not a straightforward task. You need to think of data integrity, you need to think of cybersecurity, you need to think of like how um, you're gonna see there'll be you need to hire a team who is well versed with AI. There's a skill gap that you need to watch out for. And then also you're gonna have early adopters, you're gonna have naysayers. So you need to have a solid plan and deploying the solutions and getting the agreement from your employee resource pool that they will adopt it. So for which you need to continuously and clearly articulate your vision, strategy, and roadmap for deploying the AI initiative in your company. For a junior engineer, I would say that you need to be very good with your coding, um, and then have the willingness to learn about semiconductor industry and processes or equipment, whatever that is. It's And then they should network because networking will help you get a foot in the door. So those would be the kind of insights I would give to the leaders and the um, young engineer.
Understood. Arvinder, that's certainly important as a co-founder of a company or in a leadership role. And you talked about soft skills, Arvinder. Can you elaborate a little bit more on specific soft skills and how does one develop them?
Right. So I would say PowerPoint and writing. PowerPoint because in most of the companies, unlike Amazon, which
Yeah.
believes in writing, I don't know how true is that, but most of the communication is done through a PowerPoint. And for you to hold efficient meetings, my mantra is you spend the 10 minutes presenting your content, and then the rest 50 minutes should be discussion and the help that you need. And you should have key decisions to be asked or to be made. So making a presentation will save you, or it will help you get the decision and resources that you need. Else it's a wasted time of like 5 people or 10 people who just attended the meeting. And I think the way you get better is you have to keep working on it, and you do need somebody to say whether it's a good presentation or bad. So go find mentors, look at people's slide who you like and ask them, how can I make my slide better? So I think that's how you're going to grow.
As people transition into this world now where AI semiconductor is very important and in some ways these worlds are merging today, what would be your recommendation for young engineers? How do they have impact?
The people who have had impact on me are the ones who demonstrate critical thinking, uh, who demonstrate or articulate their vision very clearly, and then if things fail, own up to it. So have ownership and accountability. Um, so I would relay the same message to other people. I'll preach what I learn. Is that take take initiatives. It's okay to be wrong. Own up to it. Don't blame it to somebody else if you fail. It's okay to fail. Um, Innovate. um, yeah, and then just ask for help. I guess the other thing I would say is that just go do it. Like, don't ask for permission, ask for forgiveness. That's another thing one of my mentors taught me. I guess I would just say these things.
Tell us more about asking for forgiveness, Arvinder.
So
Please
let's
elaborate. Yeah.
let's say you're trying to do an experiment, and for you to get the right data and you know that there is a deadline coming, and let's say you have a budget issue that you cannot order, I would say just go and order. I mean, I'm not saying order, let's say if it's like couple $1,000 equipment you want, go order it. Don't wait for your boss to say yes, right? Because if you wait, you'll probably lose like anywhere between 2 to 3 weeks. So within reasonable limits, just go order it. People may like make a big fuss about it if their budget does go beyond, but if you show the data and if it makes sense, nobody's going to question it. Now, with that being said, don't go and order like $1 million equipment. You may lose your job.
So within reasonable bounds, it's okay to break, to not follow all the rules,
right,
as long as you can get the job done and benefit.
right.
So it's okay not to obey all the rules that are set out.
Right.
Arvinder, you've experienced a lot in the semiconductor space. You've looked at R&D, supply chain, product management, leadership. What excites you about the future? For the first time, I personally feel that for the first time, we have a semiconductor company as one of the most valuable companies in the world, right? That has never happened. I find semiconductor, the future to be very bright. What excites you?
Right, definitely. I think material innovation and the equipments to enable material innovation is definitely very critical to make things happen. So I plan to continue developing and doing research in this area so we can have, devices from AR, VR to, data center chips. So you can have wearables, you can have cheaper IoTs, less power consuming IoTs. So I think I'm going to stay in this field for now.
Arvinder, I'd like to thank you for coming out today and sharing us your perspectives. This was deeply insightful. We learned a lot from you on semiconductor technology, applications of AI, a lot of great lessons for young engineers and business leaders as well. Thank you so much.
Thank you. Thank you for having me over. Yeah.